Hello, linear algebra students. This is our second extra practice worksheet, and the topics cover some of the material in sections 1.3, 2.1, and 2.2. The first question comes from 2.1. We have a linear transformation, it goes from R2 to R3, and we're given some information. We want to find T of E1, T of E2, and the matrix of the transformation. So let's start off with T of E1. I will say we are going to have to use properties here. T of E1, well, you notice we are given here, we are given T of 3E1. So this would be T of, well, we can write E1 as 1/3 times this vector, 3, 0. But now, here's where properties come. This would be 1/3 times T of this vector. And this is what's given. So this is just 1/3 times the vector 3, 6, 0, which is 1, 2, 0. So we have found T of E1. Now we have to do something similar for T of E2, except we're going to be using the other property of linearity. We have T of E1 and we have T of 1, 1. So T of E2, well, we have to think about writing E2 as a linear combination of 1, 1 and E1. We can do this by taking 1, 1 and then minus E1. This will give us exactly vector E2. Now we can just break this across a sum. As I mentioned, this is our second property of linear transformations. This would be T of 1, 1. And then minus T of E1, which we've already calculated. I like this example because not only are we asked for the matrix, which we still have to do, we have to use properties. Well, now I can just subtract these two vectors, T of 1, 1 minus T of E1. T of 1, 1 is 1, 1, 5. And then I have 1, 2, 0. And we get the following, that T of E2 is 0, -1, and 5. Now we can immediately write down the matrix because we know the matrix of a transformation has columns. Well, the first column is T of E1 and the second column is T of E2. T of E1, maybe I'll even just copy and paste, and then T of E2, we can copy and paste because we've already found these two vectors. And this is the matrix of my transformation here. That was number 1. Number 2, we're given vector X, which is in R3, vector Y, which is in R2, and we have two parts. We want to give an example of a rank 1 matrix A with AX equals Y, and an example of a rank 3 matrix B with BX equals Y, or in really both cases, explain why it's not possible if it's not. So let's think first about the size. We have vector X, we have vector Y, and vector X is 3, 2, 1. Vector Y is -1, 4. Vector X has 3 rows, 1 column. Just like I said, it's in R3, and this has 2 rows, 1 column. This is in R2. Well, I must have a 2 by 3 here. That means 2 rows and 3 columns. So it's going to be like this. 2 rows and 3 columns. Now, how are we going to find a rank 1 matrix? If we, for example, just fill in 1 column with something non-zero, and we have 2 columns of zeros, say, that would be rank 1. I could take just 1 times this column and then put zeros here. Is this the only option? Oh, definitely not. You could also put only something non-zero in this column. You could take a half times each one of these, put that in the second column. put zeros everywhere else. That would be another example, but this is perfectly fine. So here, this is our matrix A. I'll just copy and paste it to have my answer. And this is rank 1. You can see it with, really, if you want to get reduced row echelon form, just 2 row operations. Multiply this by -1, and then you can take -4 times that and add it to that. The reduced row echelon form of this matrix has a 1 here and zeros everywhere else, rank 1. Well, let's continue. In fact, I can copy almost all of this to the next line. Now I want to rank 3 matrix, except this won't work. Well, how am I going to solve this? I'm going to say this is not possible because B needs to be 2 by 3. And so the rank of B must be less than or equal to 2, cannot be 3. And so this is not possible. So here's my answer in letter A. We were able to do this. And here's my answer in letter B, not possible. Number 3, is there a linear transformation T from R3 to R such that T of 0, 1, 1 is -1, T of -1, 1, 1 is 1, T of 1, -1, -1 is 1. Those 3 things. Well, the answer is no. There's more than one way you can justify, and the justification is important. But how am I going to do this? Well, if you notice, looking at this vector and this vector, they are scalar multiples of each other. So I need to think properties here. T of. Well, let's put the minus sign. Negative, -1, 1, 1. This equals, this is one of the values we are given. Be T of 1, -1, -1. This is 1, but this is not equal to negative T of this vector here, you see? And so this fails one of our properties of linearity. This would be our justification. That there is no linear transformation from R3 to R that satisfies those 3 things. Number 4, we are moving into some geometry, and we are given a line in R2, and then we're asked for the matrix of projection and reflection for this line. Well, the first thing I need to do, you see the line I'm given as y equals 5x, but let's write it as a span. So how can I write this line as a span? Let's see, if I take x to be 1, then y equals 5 times 1. So here's writing L as a span. Now that we have this, we can just take, say, W to be this vector, and then we can immediately write down the matrix of projection, and similarly, we can use this to find the matrix of reflection. So the matrix of projection is 1 over W1 squared plus W2 squared, and then we have W1 squared, W1 times W2, W1 times W2, and W2 squared. So it looks like this, but we should make this a little bit nicer. You note that this is 26, and so maybe I'll leave the constant on the outside for the moment. I have 1 over 26, and then I have this 1, 5, 5, 25. Of course, I could pull this constant inside. Constant times a matrix. Well, we just multiply every entry by 1 over 26. But I think I'm going to leave it like that for the moment. So this is my answer in letter A. This is the matrix of projection. And now we move on. Well, we have to remember what is reflection. If we want to reflect about a line of some vector x as a function, this was 2 times the projection minus the identity. And so on matrices, the matrix is 2 times the projection matrix. This is one way to do it. Minus the identity. So I have 1 over 13 minus 1. I have 5 over 13 here. And then I have 5 over 13. And I have 25 over 13 minus 1. Now let's write this. All I have to do is add 2 numbers, and then I'm done. We have negative 12 over 13, 5 over 13, 5 over 13, and then we have 25 minus 13, which is a positive 12 over 13. So this is my answer. This is the matrix of reflection about this line. The way that I got it was 2 times the projection matrix minus the identity. Now, this is our very last one. We want to think geometrically. So it says, what is the transformation where you reflect and then you reflect again? This is function composition. So I have a picture here. In my picture, I have the line L graphed, and then I have just some vector X, and we can think about what happens when you reflect and then you reflect again. So we reflect one time, we're over here. Okay, this is the reflection. Now reflect again. Well, you see, it goes back here. So when you reflect and you reflect again, what happens is the identity map. This TR, compose TR, is the identity on R2. And we will certainly say more things about this as the semester progresses. But even now, we can think about this just geometrically, and it's fun to think about. So this is the end of our extra practice worksheet. Thank you so much.